All right. Good afternoon, everyone. It is 10:22, or actually, no, I'm sorry, 9:22 on November 30th, 2020. I am recording this in advance for this afternoon's lesson. So I apologize. I was just told that they're going to be shutting my electricity off in about an hour. So I wanted to get this recorded in advance. So I'm going to start recording and we'll go from there, and I'll post this as soon as I'm done. You may be able to hear Nevada Power and Light doing some work outside, so I apologize in advance if you do hear that. But that's them doing the work, and they said they're going to shut my electricity off at around noon today in order to do some work out there. So let's try to get through this, and then I'll post this for you guys to review on your own. So this will be an asynchronous class. So last time we spoke, we were talking about specific heat capacity, right? And when we talked about specific heat capacity, we're talking about it's the inertia of an object's ability to change temperature and change its state of motion, right? Specific heat describes what it's like for an object to either take on heat or also give off heat at the same time. We talked about that in relation to the ocean with regards to the beaches, how the water can stay warmer than maybe the beaches may stay because the water's specific heat is different, right? Property of water to resist change in temperature improves the climate in many places, right? Because the water is very useful as cooling agent in cooling systems, automobiles, and other engines, right? A lower specific heat capacity temperature would rise for comparable absorption of heat. Water takes longer to cool. Water's capacity to store heat affects global climate, right? When you think of the west coast of the United States specifically, because it's extremely, the whole length is bordered by water, it has a much milder climate because of that. And same thing with Europe and most of Europe, because it's surrounded by water, right? The climates on the East Coast and West Coast of North America differ, right? The prevailing winds latitudes are westerly, meaning the winds are going to move from the west. On the West Coast, air moves in from the Pacific Ocean across the land, right? In winter, the warm water warms the air and moves over and warms that western coast of North America. In summer, the water cools the air, right? And therefore, it's a little bit cooler on those coasts. On the East Coast, the air moves from the land to the Atlantic Ocean, right? So therefore, the heat's going to be leaving the land. So land with lower specific heat gets hotter in summer, but cools rapidly in winter. When you look at DC and San Francisco, they're on the same latitude, right? But San Francisco has a much milder climate, right? The central of the interior continent is one of the areas that experiences extreme changes in temperature when you think about it, right? That's where we get the Rockies and everything, and that's why they have more snow than most of the rest of the country on top of the altitude, right? Expansion. Most forms of matter, we talked about this, solids, liquids, and gases, expand when they're heated and contract when they're cooled, right? When the temperature of a substance is increased, its molecules start to jiggle faster, which this is the only time we'll ever use jiggle in science, and then tend to move further apart. The result is an expansion of the substance. Gases generally expand or contract much more than liquids, right? Because their molecules are already farther apart. That's why they're gases. And liquids generally expand or contract more than solids, solids being the most difficult to expand or contract. There's this thing called a bimetallic strip where two strips of different metals are welded or riveted together. When one strip is heated by the other, the one side becomes longer, causing the strip to bend in a curve. When the strip is cooled, it bends in the opposite direction. Why is this important? Well, they use this in the old style thermostats, right? Or what they call a traditional thermostat, not one of your Eco or Nests or any of those. They have a little strip in them that bends as the temperature changes. And as those bends occur, it'll turn on your heat or turn on your air conditioning or do nothing based upon the bend of the actual bimetallic strip. So then why is it advisable to leave telephone lines sagging when stringing them? Well, telephone lines are longer in summer, obviously, because when things heat up, they expand, and then shorter in winter. So that sag on more summer days they sag more on summer days than they do in winter. If telephone lines aren't strong with enough sag in summer, they might contract too much during winter and snap. Plus, those lines are in full tension when the birds land on them. That could cause all kinds of problems for us, right? So when we talk about water being unique, we'll throw a joke in here, right? How do you catch a unique rabbit? Well, of course, unique up on it. And then how do you catch a tame rabbit? Tame way, unique up on it. Okay, so my jokes aren't the best. I appreciate, at least I try to work some of them in. At 0 degrees Celsius, ice is less dense than water and therefore floats on water. So this is why we say that water is unique as a substance. It doesn't react the same way as other materials. At 0 degrees or at cold temperatures for other substances are going to be more dense than they would be at liquid. Almost all liquids will expand when they're heated. Ice water, however, does the exact opposite. Water at the temperature of melting of ice, 0 degrees, contracts when the temperature is increased. As the water is heated, temperature rises and continues to contract until it reaches a temperature of about 4 degrees. At 4 degrees Celsius, water is the most compressed it can be. Then, once you cross that 4 degrees Celsius and start going up, water starts expanding. Temperature continues to occur until the water reaches its boiling point. So a given amount of water has its smallest volume and therefore greatest density at 4 degrees Celsius. The same amount of water has the largest volume and smallest density in the form of solids or ice. The volume at 0 degrees is not shown on the graph that we showed before, right? After water is turned to ice, further cooling will cause it to contract. So if we keep cooling it down even further past 0, it will eventually contract. Well, why does water act like this? Well, up in the corner, I've got a picture of the water matrix, right? Which is a crystalline subject. Ice has open structure crystals due to the shape of the water molecules and the strength of the forces binding H2O, right? The water molecules in this open structure occupy a greater volume than they do in the liquid state, and that's why things look a little bit differently. When ice melts, crystals remain in the ice water, forming a microscopic slush that slightly bloats the water. Ice water, therefore, is less dense than slightly warmer water. With an increase in temperature, more of the remaining ice crystals collapse. The melting of the ice crystals further decreases the density, right, in the volume of the water. When you look at that picture at the bottom, that kind of is a great example of how water, when it freezes, forms a very unique crystalline substance, right? Snow is an excellent example of that. No snowflakes are alike. You've probably heard that. So this is really important in nature, right? Suppose the greatest density of water were at its freezing point. It's true of most liquids. And the coldest water would settle to the bottom and ponds would freeze from the bottom up. Well, then anything in that pond would die, right? Because in the winter months, there'd be nowhere for it to hide. So therefore, the densest water settles at the bottom of the pond. It's about 4 degrees Celsius. And therefore, those plants and organisms that live in those ponds and lakes can actually adapt and live at that 4 degrees Celsius. Water at the freezing point is less dense and starts floating up. Therefore, the ice forms at the surface while the pond below remains a little bit warmer and more hospitable to life to make it through winter. Most of the cooling in a pond takes place at the surface, where the surface area is colder than the water. So as that surface water is cooled, it becomes denser and sinks to the bottom. The water will float to the surface for further cooling only if it's as dense as or as less dense than the water below. So if you have a pond initially at 10 degrees Celsius, it obviously can't be cooled to 0 degrees without first passing 4 degrees. At 4 degrees, water can't remain on the surface because it's too dense, and therefore it's going to sink to the bottom, right? So that sinking or 4 degrees Celsius water is where, all your fish and all your plants are going to survive throughout the winter. This is why, when you look at a lake that might have fish in it, the fish don't die instantly over winter. They migrate down to the lower portions of the lake, which are slightly warmer. And because of their own body chemistry, they can survive at those temperatures. Therefore, the water surface is the first to freeze. Continued cooling of the pond results in the freezing of the water down next to the ice. So the pond freezes from the surface downward. In a really cold winter, I know we don't have this here, but where I'm from, we do, especially for ice skating and stuff. The ice will be thicker in a milder winter, right? Very deep waters of body, maybe not even ice covered at all. We've only had, in the area I'm from, we have the big Susquehanna River. It's pretty rare that the whole surface of the river is ever frozen. There's usually a channel in the middle that's running pretty rapidly, and that doesn't freeze over because of the impact of the molecules on each other heating up that area. And all the water in that lake that we're looking at must be cooled to 4 degrees before lower temperatures reach. And that's why that bottom of that pool is going to, or that bottom of that lake is going to stay at 4 degrees Celsius. So these are the assessment questions for this chapter. Go ahead and look through them. I'm going to switch to the next lesson here real quick. Stop share, and we'll go to the next lesson. So we're going to tie the next lesson into that lesson. The next lesson is going to be on thermodynamics, or the flow of heat, right? So share screen, or share thermodynamics. All right, so now we're going to talk about thermodynamics. Talk about through the laws of thermodynamics. So there are 3 different laws of thermodynamics as we go through this, right? First of all, we talk about the transfer of heat. There are 3 main different transfers of heat. There's conduction, convection, and radiation. Conduction is the transfer of heat, excuse me, when materials maintain direct contact with each other, right? Materials that conduct heat well are known as heat conductors. Convection is transferred by movement of a heated substance itself, such as currents in a fluid. And then radiation is energy transferred by electromagnetic waves. So putting this in physical therapy terms, conduction of heat is when we put a hot pack on a patient. So the object come in contact with each other, the hot pack and the human skin, well, not directly, hopefully there are layers between them. We'll talk about that in modalities. And that contact is going to conduct the heat from the hot pack to the body. Convection. The best way you can think about a convection is those convection ovens you see, right? Whether it's the full-size oven or those smaller convection ovens. The convection is the air around it becomes almost fluid-like as it moves in a current, and that current of air constantly flowing around that substance will heat that whole substance up. And it allows for a more thorough cooking if you have a convection oven, right, than just a traditional element oven, which relies on a little bit more of radiant and conduction of heat. Radiation would be something we think about when we're using something like a microwave, right? A microwave is going to send electromagnetic waves into your food and heat up from radiation. Here on the Earth, we're radiated by the sun, and so that sun provides us with the heat here on Earth. So the study of heat and its transformation in mechanical energy is called thermodynamics, right? Thermo meaning heat and dynamic meaning movement. So the foundation of thermodynamics is conservation of energy. It's also that we know that heat flows from hot to cold. It provides the basic theory of engines, which we run on, right? So first of all, we talked about this before in the last lesson. We'll hit it again here. Absolute zero, right? Absolute zero is the point where no molecular movement is occurring. As a substance approaches to zero, the kinetic energy of the atoms approaches zero, and the temperature of the substance approaches its lower limit. As the thermal motion of atoms increases, temperature increases, right? There seems to be no upper limit of temperature, but there is an opposite end when movement decreases, right? If we continually decrease the thermal motion of atoms, the temperature will drop. That absolute zero is which no more energy can be extracted from a substance. Theoretically, at that point, the object may even be stripped of electrons. We're not even sure what truly happens at sub-zero, or that absolute zero temperature, right? No further lowering in temperature is possible. It's about 273 degrees below zero in Celsius, right, or 0 K. Unlike Celsius, in the Kelvin scale, there is no, or the thermodynamic scale, there is no negative numbers because zero is as low as you can go. So in the Kelvin scale, ice melts at about 273 and water boils about 373 Kelvin. But absolute zero is down there where the lowest possible thing we can go, right? And we have different temperatures, right? So at about 373 or about 400 K, the water boils, right? Tin melts at about 500, 1800 is about iron melting. And we get that whole chart on the side. The surface of the sun is 6,000 Kelvin. We know that we have plasma, hot stars, the center of the sun, and we know that a hydrogen bomb, when it goes off, emits temperatures of about 100,000, or actually 100 million Kelvin. So that explains why things, when a bomb goes off, nuclear bomb, are what we call atomized, because at that temperature, our atoms are no longer going to be held together and they're literally going to blow apart, right? If you see pictures of anywhere where an atom bomb was dropped, at the impact site or the crater site where that occurs, there's pretty much nothing left. So we have a sample of hydrogen gas at a temperature of 0 degrees. If the gas is heated until the molecules have doubled their average kinetic energy, the gas has twice as amount of the absolute temperature. Excuse me. What will the temperature be in degrees Celsius? Well, at 0 degrees, temperature has an absolute temperature of 270 Kelvin. If we double that kinetic energy, right, that means we're going to double the kinetic temperature. So that means it's going to go to 546 degrees Kelvin. If we convert that to Celsius, that's going to be 273 degrees Celsius. So the first law of thermodynamics says that whenever heat is added to a system, it transforms into an equal amount of some other form of energy. In the 18th century, heat was thought to be this invisible fluid called caloric, which is where we got the term calorie from, which flowed from water from a hot object to cold object. So in the 1840s, a guy came along named James Joule, which, yes, that's where we got the joule from, and demonstrated the flow of heat was nothing more than the flow of energy. The caloric theory of heat was gradually abandoned from then on, although we kept the term calorie because it really helped describe the transfer of heat. So today we actually do view heat as a form of energy, and we know that energy can neither be heated or neither created nor destroyed. And so therefore, the first law of thermodynamics is the law of conservation of energy applied to thermal systems, meaning that when you add heat to a system, it can't escape. It doesn't really go, the object is either transforms into an equal amount of some other form of energy, or it does some work on the object, right? When we talk about a system, we're talking about a group of atoms, molecules, particles, or objects that we wish to deal with. The body would be a system. System may be something like steam in a steam engine, the whole Earth's atmosphere, even the body of a living creature. It's important to define what's contained within the system as well as what's outside of it. So when we add heat energy to a system, the added energy does one of two things, or both, right? It increases the internal energy of the system if it remains in the system. It does external work if it leaves the system, or it can do a combination of increasing energy and doing work. So the first law of thermodynamics states that if we add heat added to a system, it's going to increase the internal energy plus possibly do external work by the system. So let's say you put a can full of air, one of those compressed cans of air, rigid, airtight, onto a hot plate, and then you turn the heat up. Now, caution, do not do this. This would be bad. The can has a fixed volume. Those walls can only expand so much, right? So no work is going to be physically done on the can, especially if we have a can that's very rigid. So say you have a steel can or something to that effect. The walls won't move, so no work is going to be done. If those walls move, slight amount of work will be done. That means all heat going into the can is going to increase the internal energy of the can in the enclosed air. Internally, and actually externally too on the outside of the can, temperature is going to rise. Eventually, that internal energy that heat added to the system will no longer be able to be contained by the walls of the can, and well, boom, the can's going to explode. Because now all that energy inside the can has enough energy to do work on the system and push out and explode the walls of that can. So now let's say we replace that with a balloon, right? The air is heated as it expands, exerting a force on the distant surrounding atmosphere. Some of the heat added goes into doing work, so less of the heat goes in to increase the enclosed energy, right? The temperature of the enclosed air will be lower than that of the air in the closed can. So if we heat up a balloon, it will do some work on the outsides, even if we don't fill the balloon up fully, right? So maybe we fill it up half full, and then we heat up the balloon. The balloon is actually going to expand. That's work being done. There's still going to be an increase overall in temperature inside that balloon, but the temperature won't increase as much as, say, that can would, or as rapidly. So steam engines, this was like a major development in our, progress as a humankind, right? The steam engine helped us get things cross-country, cross-continent, all that fun stuff. And it uses a given quantity of heat supplied to a steam engine. The heat increases the internal energy of the steam, right? The rest is transformed into mechanical work as the steam pushes a piston outward. Those pistons cause compression in the engine, much like the engine in a car, which then rotates the drive shaft and allows the train to choo down the line, right? That's how Thomas becomes a very useful engine for those of you that are parents. So the first law of thermodynamics is just the thermal law of conservation of energy. We talked about that. So adding heat is not the only way to increase the internal energy of a system. If we set the heat added part of the first law to 0, changes the internal energy equal to the work done on or by the system. So if we have no heat added to a system, but a specific system does work, then the internal energy is going to decrease. Think about that with your body, right? If you go and work out, your internal energy is going to go down. You didn't actually add heat to your body, right? But it is going to increase the exterior temperature of your body, but not the interior, right? But your overall energy stores are going to be reduced. That's the law of thermodynamics, right? The only diet that follows the law of thermodynamics is calories in have to be less than calories out. That follows the law of thermodynamics, because what it's saying is if you decrease the amount of energy taken in and increase the amount of energy taken out, you create a caloric deficit, and therefore you lose weight. What happens if we take a balloon and we squeeze it really hard? Well, when we squeeze it really hard, we're not adding heat to the system. What we're doing is adding pressure. That pressure is work being done on the molecules inside. If we were able to actually do an infrared picture of that balloon, you would see that inside that balloon, the temperature inside that balloon would actually increase, right? That's that work being done in the system. So if 10 joules of energy is added to a system and does no external work, the internal energy is obviously going to go up by 10 joules. What if 10 joules of energy are added to a system and it does 5 joules of work? How much has the internal energy been raised? Well, at that point, you have 10 joules added, 5 joules done. That means the internal energy is going to go up by 5 joules. So the adiabatic process. So please understand this is the adiabatic process, not the adiabetic process. The adiabatic process or adiabatic process is where you eat too much sugar and you become a diabetic. I'm just joking. Says that when work is done on a gas adiabatically by compressing it, the gas gains internal energy and becomes warmer, which is what I just talked about with that balloon. So when a gas is compressed or expanded so that no heat enters or leaves the system is said to be adiabatic. So you can think about this like a bicycle pump. If you were pumping up a tire on a bicycle or pumping up a basketball, the pump itself, right? You pull up on the handle and you push down. What you're doing when you're pushing down is pushing down on a piston that is compressing the air in the cylinder. It is doing work on that air. And that air, therefore, is gaining internal energy. Now, most of it will escape via the bottom portion of that canister and go into the basketball or whatever you are. If you actually look at the temperature of both the canister and the basketball after pumping them up, the temperature in both of those will have gone up because you have processed an adiabatic change. Adiabatic change of volume can be achieved by performing the process rapidly so that heat has little time to enter or leave, and therefore thermally insulating system from its surroundings, right? Great example of this is the compression and expansion of cylinders of gases in a compression engine, right? Compression and expansion occur in only a few hundredths of a second, too fast for heat energy to leave a combustion chamber, therefore it releases the energy. The higher the compression, like those in diesel engines, the temperature can be high enough to ignite the fuel mixture without a spark plug. That's why diesel engines have no spark plugs. It can also be why it's very difficult to get a diesel engine to restart once you've run out of fuel, because that compression requires a little bit of energy as well. So we got a picture here of your common engine, right? Now, this is like most of your engines you have in the world, right? So the intake, the air fuel mixture fills in the cylinder as piston moves down. The piston moves up, compresses the mixture adiabatically, right? So it squishes it, and it increases the internal energy of that mixture of air and fuel. And then the spark plug fires off. When that spark plug fires off, it raises that temperature rapidly. That rapid expansion then causes the power stroke. The expansion pushes the piston down. That piston pushing down then is actually going to go ahead and be pushed out via the exhaust valve. I can speak today. And the cycle is going to repeat itself. All of that's going to occur and then also turn your drive shaft. As your drive shaft turns in your car putter-putt-putts down the road. So if you have a higher compression engine, it may require less spark or may create more energy, depending upon what you're looking for. So this is why, in really, really high compression engines like those in the really, fancy high-end cars like Ferraris and Lamborghinis, they're able to achieve such horsepower in it because they're able to actually compress that gas so much, the gas in the air fuel mixture, that they maximize that energy exchange and are able to actually get a higher adiabatic result out of it. So a little humor here again. If you run behind a car, you're likely to become exhausted. If you run in front of the car, you're likely to become tired. Get it? It's kind of funny. I thought it was. The atmosphere is actually an adiabatic process at work, right? We have masses of air that change temperature as they go along, right? We call these masses the air blobs. As a blob of air flows up the side of the mountain, the pressure lessens, allowing it to expand and cool. The reduced pressure results in reduced temperature. As temperature of a blob in the air expands adiabatically, about 10 degrees Celsius for every kilometer it goes up. So, if at Earth's surface, the temperature is 56 degrees Celsius would be hot. Let's say it's 30 degrees Celsius. If you go to Mile High City, which is, 2 miles, or it's a mile high, right? Which would be about 1.8 or 2.2, I can't remember, 1.8 kilometers, I think is what it is, 1.6 kilometers. The temperature would actually be about 15 degrees different in Denver than it would be in a comparable plain city because of the change in the air compression, right? That air flying over cool mountains may result in thunderstorms or cyclones that change in elevation by several kilometers. This is called the Chinook. So air at 25 degrees ground level would be negative 35 at 6 kilometers. If the air at negative 20 degrees has an altitude of 6 kilometers descended to the Earth, its final temperature would be a roasting 40 degrees Celsius. So as air rises and falls, it changes in temperature, and that's what changes our climate. So this Chinook idea, right? This is the warm, dry wind that flows from the Rocky Mountains across the Great Plains. The cold air moving from the slopes of the mountain is compressed into smaller volumes and is appreciably warmed. Communities in path of the Chinook experience relatively warm weather in midwinter, while the Rockies themselves may stay super cold. So the second law of thermodynamics states that heat will never itself flow from cold to hot, right? We talked about this briefly in heat. A hot brick is next to a cold brick. The heat is going to flow from the hot brick to the cold brick until both bricks arrive at thermal equilibrium. If the hot brick were to steal energy from the cold brick and actually make the cold brick colder, this would violate the second law of thermodynamics and doesn't happen naturally in the world, right? The second law of thermodynamics describes the flow of heat. So it's always going to flow from hot to cold. Heat only flows one way, like I said, from hot to cold. In winter, heat flows from the inside of a warm heated house to the cold outside. My dad used to say this all the time during summer. He'd be like, you'd open the door, he'd be like, what are you trying to do? Cool the outside? Well, technically, no, that's not the way it would work. What you're really going to do is warm the inside, because the inside air is cold, the outside air is warm. It is going to steal some of the heat from the outside air, and it's actually going to warm up the interior that way, right? This is why we try to insulate our houses. In summer, heat flows from the hot air outside, which is what I was talking about, to the cooler interior. Heat can be made to flow the other way, but only by imposing external effort or energy, such as heat pumps. That's how those heat pumps work in your houses. When we look at the ocean, there's a huge amount of internal energy in the ocean, right? All this energy can't, though there's this huge energy, it's not able to light a flashlight lamp because it doesn't have external effort, right? Energy itself will not flow from the lower temperature ocean to the higher temperature lamp filament because that's not the way energy works. Energy is always going to flow from hot to cold. So no heat engine can convert all heat input to mechanical output. That's kind of a law of thermodynamics here that goes along with second law. It's easy to change your work into heat, right? So if you want to change your work into heat, if you rub your hands together rapidly, you're doing work on the skin of your palms. That work, therefore, is then changing into heat friction, right? However, changing heat completely into work can never fully occur. The best that can be done is conversion of some heat to some mechanical work. So when we talk about this, we talk about heat engines, right? A heat engine is any device that changes internal energy to mechanical work. The basic idea between a heat engine is that mechanical work can be obtained as heat flows from higher temperatures to lower temperatures. Excuse me. Some of the heat can be transformed into work in a heat engine. So consider we talk about reservoirs. If we picture a high temperature reservoir as something coming from where you can extract heat without cooling it down, a low temperature reservoir is something that can absorb heat without warming up. Heat will flow from a high temperature reservoir in a heat engine to the low temperature reservoir. That heat flow itself, moving from that hot area to that cold area, can be used to drive things like pistons, fans, anything along those lines, turbines. And then we can use that change some of that temperature flow into mechanical work. So every heat engine will increase its internal energy by absorbing heat from a reservoir of higher temperature, convert some of its energy into mechanical work, and expel the remaining energy as heat to some lower temperature reservoir. Your air conditioner is a great example of this, right? You have the coolant, which is your low temperature reservoir. And then you have your engine of the actual air conditioner itself, which is your high temperature reservoir. It's going to pull the heat out of your house, compress that high temperature heat, run it through a low temperature area, and it's going to cool your house. When heat flows in any heat engine from high temperature place to a low temperature place, part of that energy is going to transform into work output. According to the second law of thermodynamics, no heat engine can convert all heat input to mechanical energy, meaning they can never be 100% efficient. Some of it is still going to be released as external heat. And I don't know why I duplicated that slide. I apologize. So the French engineer Sadi Carnot characterized and carefully analyzed the heat engine and made a fundamental discovery. The upper fraction of heat that can be converted into usable work, even under ideal conditions, depends upon the temperature difference. So the hotter the hot reservoir, the colder the cold reservoir, the more efficient the engine, right? This is what we talk about with Carnot efficiency, or ideal efficiency of a heat engine. It's a maximum percentage of input energy that engine can convert into work. So no engine will ever be 100% efficient. If you look at something like an air conditioner or a heater or a heat pump or even a car, there's going to be an efficiency level of that heat engine. So the higher we can create the high temperature reservoir, and the lower that we can have that lower temperature reservoir, the more efficient the engine can become. Well, doesn't this just also explain why your car is more efficient at burning gas when it's cool out than when it's hot out? Yeah, it does. Because your exhaust reservoir, where the exhaust is eventually going to go, is cooler during a cold temperature snap, such as we're having now, and your engine's still going to be as hot as it always is, right? So therefore, that flow of gases going through your engine is going to become more efficient, and therefore your car itself is going to be more efficient. But no engine, as we discussed, is ever going to be 100% efficient. Carnot's equation states the upper limits for efficiency on all heat engines. The higher the operating temperature of any heat engine, the higher the efficiency. Only some of the heat input can be converted to work even without considering friction. So then we go to the third law of thermodynamics, and it's kind of a rare talked about one, but it makes sense. The third law states that no system can reach absolute zero. No heat engine, no air conditioner, car, blah, 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 can ever reach absolute zero. If it did, it would never be able to do work, because at that point, no molecules are exchanging anything, right? Investigators attempt to reach this lower temperature. It becomes more and more difficult as you get closer and closer to it. We've been able to get to about a millionth of a Kelvin, but never as low as 0 Kelvin. And I talked about this last time. I'm not sure that we really want to reach 0 Kelvin, because I'm not sure what would happen if we were able to actually do that, right? It's just like we're not sure what will happen if we combine matter and antimatter. They're still trying to figure out what happens, but we really don't know, do we? So chaos theory, or order towards disorder theory, right? This is the big thing that in the original Jurassic Park you saw, right? That natural systems tend to proceed towards a state of greater disorder. The first law of thermodynamics states that energy cannot be created nor destroyed. The second law states that whenever energy transforms, some of it degenerates into waste heat, unavailable to do work, right? And the third one, which we just talked about, is you can't reach absolute zero. So all of these state that an organized usable energy will always degenerate into disorganized non-usable energy, right? Then it's not going to be available for use for the same work again. right? So organized energy in the form of electricity that goes in electric lights in homes does generate heat. Even your most efficient LEDs still generate a small volume of heat. It's very, very minuscule compared to something like a traditional incandescent light, right? But it does generate some heat. The electric energy in the lamps, even the part that briefly exists in the form of the light, turns into heat energy. So therefore, you really can't fully, if you're taking in a 110 volt or 110 volt current, ever transform all those joules of energy that are coming in via that current into full light. It just is impossible because you're going to give off some heat. That energy that degenerates into heat is of no further use. Now, the Transamerica Pyramid in San Francisco and some other buildings use that to their advantage. They actually use that electric lighting and the temperature change in those lights to heat the building. So that's why the lights are on most of the time, is because that energy, they actually don't have an HVAC system that heats the building. They rely strictly on the lighting itself to heat the building. So the more lights they have, the warmer that building will be. So they tend to leave their lights on all the time. It's a really neat place to visit if you ever get a chance. So the quality of energy is going to be lowered with each transformation. As you transform, as you continually transform, that organization is going to tend to more and more disorganized forms, right? So if you imagine a room that's closed, right? And then in that room, there's a closed jar filled with argon atoms. If you lift the lid of that jar, and the only thing in that jar is argon atoms, the argon atoms are going to move in haphazard directions, eventually mixing with the air in the room, right? Therefore, at the end, all the molecules that were in that container now are gone. Boom. All right, Mr. McKeever's got jokes. The system moves from that more orderly state, all those atoms in a jar, to a more disordered state, the argon spread throughout the room. Excuse me. The argon atoms do not spontaneously just decide, hey, let's go back into that jar and hang out. No, they're going to move towards disordered containment. The number of ways the argon atoms can randomly move, the chance of returning to the ordered state is practically zero. Now, does that mean that there won't be any argon atoms in the jar? No, absolutely not. There will be argon atoms in the jar. It's just they won't be the same concentration of argon atoms in the jar. And those atoms won't spontaneously decide to jump back into the jar. They're going to continually move out in chaotic manners, right? According to the second law of thermodynamics, in the long run, entropy of a system always increases for natural processes, right? The entropy is the measure of the amount of disorder in a system. Disorder increases as entropy increases, right? Have you heard about entropy? It's not what it used to be. Well, that's kind of a joke because it makes sense, because entropy is never going to be the same as it was previously. So rundown house or rundown barn demonstrates entropy. So what would happen, right? If in your house, you decided today, I'm not going to clean until next year on this date of November 30th. Would your house be a disaster? Absolutely, right? Because order trends towards disorder. So how do we prevent order from trending disorder? Well, we do work on it, right? We keep the house clean by picking up after ourselves. But if we do no work on our house, the house will become a mess just naturally, right? Dust will settle. Some things will break down if we don't maintain them, you know, especially if your clothes don't get washed. Well, that'd be nasty, right? But everything overall will trend towards disorder. Entropy normally increases in physical systems. However, when there is work input, such as living organisms, entropy decreases. If we didn't do work on our own bodies, the entropy would decrease, right, or would increase. Bone and osteoporosis is an excellent example of entropy. As weight bearing decreases, the bone itself is going to deteriorate or break down, trend towards disorder. If we start weight bearing and walking on those bones and doing work on those bones, we can reduce the effects of entropy and reduce the overall effects of our bones breaking down. All living things extract energy from their surroundings and use it to increase their own organization. This order is maintained by increasing entropy elsewhere, right? For the system, life forms plus their waste products, there is still a net increase in entropy, no matter what we do, right? No matter whatever we want to do, there's always going to be an increase in entropy in nature, right? Think about it. If you look at maybe even something like the Lake Mead, right? No matter what we do, even if we wanted to pump water back up into the lake, there's already been an effect of entropy where we've lost part of the lake. There's been a disorder of the lake, right? So there's an age-old question that said, how do you unscramble an egg? Well, you feed it to a chicken. That's the way you actually would unscramble an egg. You won't get the original egg back, but one will be created. Doesn't sound exactly pleasant for the chicken because technically that makes the chicken a cannibal, but hey, I mean, cannibal chickens, that's about what we expect now for 2020, right? I would ask questions, but it is 2020. So the first law of thermodynamics is a universal law of nature for which there are no exceptions that have been observed. The second law, however, is a probability statement, right? Disordered states are much more probable than ordered states. Even the most improbable states may occur and entropy spontaneously decreases, right? Haphazard motion of air molecules could momentarily become harmonious in a corner of a room. This is possible, right? There may be, for whatever reason, in one corner of a room, suddenly it's all oxygen molecules. We don't know why that happens, but sometimes it just happens. Eventually, though, those will disorder and become chaotic, right? Barrel of pennies, you could dump that on the floor and it could show up all heads. Unlikely, you'd be better off going to, down to play Keno and winning $1 million, right? A breeze may come magically into your bedroom and clean up your bedroom, but it's not likely. The odds of these things occurring are infinitesimally small, so just super small. It's probably not going to happen, right? So the law of thermodynamics are sometimes put this way. You can't win because you can't get more energy out of a system than you put in. You can't break even because you can't even get as much energy as you put into an object, and you can't get out of the game because entropy is always in the universe and is always increasing. So radioactive decay is a great example of this ordered disorder theory, right? Radioactive decay is where radioactive materials slowly break down as molecules and eventually break down into a more stable substance. So the joke of the day here, the big cat question is, does a radioactive cat have 9 or 18 half-lives? Get it? Because it normally has 9 lives, so 18 half-lives. I'm so funny. Love my jokes. So that brings us to climate change. And this is not a political statement, right? So whatever political spectrum you exist on, please do not take that I am using this as a political statement. This is just science. 99.9% of all scientists agree on climate change. The other 0.1%, I would struggle to say, I would struggle to say that their science is flawed because something's going on if they're saying that climate change doesn't exist, right? The new unanimous view of climate scientists is that human activity is the main driver of climate change. Now, that does not say, please note, that does not say that climate change doesn't occur naturally. It does. Ordered states tend towards disorder and then occasionally can become more ordered, but it's very small that happens. So climate change will occur naturally. We are just exponentially speeding it along, right? An automobile sitting in the bright sun on a hot day with its windows rolled up can get really hot inside, right? This is an excellent example of the greenhouse effect, right? The greenhouse effect is the warming of planet's surface due to the trapping of radiation by the planet's atmosphere. So as we increase our carbon dioxide and our monoxide and our methane emissions, we're actually basically creating a shield on the outside of the Earth, and it's a one-way shield. It allows energy in, but doesn't allow energy to re-escape. And by doing that, we're warming up the world, right? All things, including the Earth, radiate, and the frequency and wavelength of that radiation depends upon the temperature of the object emitting radiation, right? I'm sure you've known this. You've known friends or maybe even yourself that are warmer than other people. I'm one of those people. I don't like being in a hot environment because I'm already warm to begin with. So I'm radiating at a specific frequency of radiation. Everyone does. All people radiate, all devices radiate, all, even your cell phone radiates a certain amount of radiation, right? We've heard about that before. Do cell phones cause cancer? Well, maybe. There's some studies out there that have shown that they can tell what pocket you carry your cell phone in traditionally by looking at the damage on your hip. So it's kind of interesting. I'll have to find that study for you guys. So the transparency of such things as air and gases depends upon the wavelength of radiation. So for that hot car example, how do we prevent the car from being so hot? Well, what we can do is either A, allow more heat to escape the car than gets in. So let's say the sun beats down on the car, we change the direction of the wavelength of the glass so that more heat is able to escape the car than stay in the car. That would be one way. We can also put reflective tint on the car that prevents that sun ray from getting inside the car. Or we can do a combination of both with like ceramic tinting, where ceramic tinting will reduce the overall effect of the radiation coming into the car, but also then won't disallow that radiation to escape, right? We can also crack the windows in the car. So now we're really increasing, because now we're increasing the entropy inside the system. That energy is going to come in through the sun, heat up the interior of the car. Maybe we have that ceramic tint to prevent so much of it from getting in. And then we have the windows cracked, so the radiation actually has a better chance to escape the car. So if the air contains extra carbon dioxide, water vapor, methane, etc., it absorbs the infrared waves, right? Glass is transparent to visible light, but also absorbs infrared waves. This is why something like an infrared oven cooks food really effectively, because it's going to be absorbed by the food. So why does a car get so hot in bright sunlight? Well, the wavelengths of the waves from the sun radiate are very short. Those short waves easily pass through the car's Earth's atmosphere and through the glass windows of the car. As the sun's energy gets into the car's interior, where except for some of the reflection, it's absorbed, right? So think of your leather seats, your leather dash. All those are great conductors of heat. They all absorb heat very well. So they're going to absorb heat. They may not transmit heat very well, so they're going to continue to absorb it. The interior of the car is going to warm up. The car's interior radiates its own waves, but since it's not as hot as the sun, the radiated waves are longer in wavelength and therefore don't pass out as much. The re-radiated longer wavelengths encounter the glass windows that aren't as transparent to them. Most of that re-radiated waves remains in the car, which makes the car's interior even warmer, which we talked about by adding certain forms of tint to the car. The same idea happens in the Earth's atmosphere, right? The atmosphere is transparent to solar radiation. The Earth's surface absorbs that energy and radiates what's called geotropic radiation, right? Or radiation from the Earth. The atmospheric gases, mainly cooler water vapor, carbon dioxide, and methane, absorb and re-emit the long-wave terrestrial radiation or earthbound radiation back to Earth. So, when we've got the Earth here, so we use blue as our Earth, right? So let's get a circle. So here's our Earth, right? Actually, let's change that. Clear all drawings. Let's make it green. So here's our Earth, right? Around our Earth, we have an atmosphere. There's our atmosphere. So as the sun's let's make it yellow for sun. As those sun's wavelengths come in, they're very short, and they're able to get down here to Earth. They would be able to bounce back right out away from Earth if they wouldn't get absorbed. But unfortunately, they get absorbed, right? And the wavelength becomes longer. And because they're longer, they hit this atmosphere and are like, nope, I can't escape that. So they're redirected back to Earth and then redirected back up. And then they just bounce inside our atmosphere. And as they bounce inside our atmosphere, the temperature of the Earth is going to go up, right? So without this warming process, so if we didn't have this process, we didn't have our atmosphere, the Earth would be minus 18 degrees Celsius at all times, in all corners of the Earth. That would be pretty cold, right? So we need a little bit of this process to maintain our temperature and our heat. But as increased levels of carbon dioxide and other atmospheric gases in the atmosphere may further increase this temperature. So we could further increase it as we go along, produce new thermal balances unfavorable to the biosphere. There are some studies that have shown that within 10 years, the average summer temperature in Las Vegas could be 135 to 140 degrees Fahrenheit. That's hot, right? That's actually potentially unlivable hot, because that's energy grid failing type temperatures there. Phoenix, same thing. Well, why is that? Well, because we're in a desert, obviously. But that's not the major problems we have. One of the major problems we have is as these heat temperatures go up, right, our poles, which are primarily comprised of ice, begin to melt. That melting ice has to go somewhere. And we learned about in last lesson, that water is most dense at about 4 degrees Celsius. So as that ice breaks out and forms slush, it's going to increase the density of the oceans of the earth. Therefore, it's going to push those oceans further up onto land. And we're going to lose more and more land, right? Maybe as soon as 2050, maybe as soon as 2060, most of New York may be underwater. Almost all of Florida will be underwater. Now, does that mean that this wouldn't have occurred naturally? No, I mean, it's possible this could have occurred naturally, but maybe not for thousands of years. This is what people will try to argue is, well, Florida would have sunk in the ocean anyway. Yeah, it would have. But if thousands of years from now we're going to see it within a human's lifetime. That shows you how drastically we've actually changed our climate. We have structurally changed the function of Earth's climate. So Earth's temperature depends upon the energy balance between incoming solar radiation and outgoing terrestrial radiation. The atmosphere acts as a one-way valve. It allows heat in, but necessarily doesn't allow heat out. It allows visible light in, but then that terrestrial radiation, which is non-visible light, doesn't escape. After a few years, solar radiation strikes the Earth, balances the terrestrial radiation, and emits into space. So the Earth does warm the space around it, right? Not appreciably, you're not going to notice it because, again, once it escapes into space, space is such a wide open, non-molecule containing object, vacuum, that the objects are going to spread so rapidly, you're never going to find them again, right? So appreciably around the Earth, temperature doesn't really change in space, but it does emit some of that terrestrial radiation. So we do have average temperatures of Earth, right? We've been able to track average temperatures of Earth as far back as millions of years. And we know what happens during ice ages. We know what happens during these times of global climate warming. And if you look at what will eventually happen is we'll end up with these periods of global climate warming and eventually end up back into another ice age. Because storms will kick up. Those storms will get very, very cold over high altitudes, also over those northern poles, southern poles. And it'll eventually freeze a large portion of the world. And I always laugh because there was a senator once that came into Washington, D.C., and he was carrying a snowball. And he threw it on the House floor and said, if we've got climate change, then what is this snow doing here? What he doesn't realize is he just proved climate change. Because as the Earth warms up, climate is going to become more and more unstable. Right? And that means that weirder weather patterns are going to happen. Are we seeing that already? Absolutely, we're seeing that already. Look at the quality and the strength of the hurricanes that we see hitting the coast, right? Those hurricanes are becoming greater and greater in frequency and greater in magnitude. When was the last time you remember us exiting out of the naming system and going into naming hurricanes based upon Greek lettering? I don't ever remember that, and I'm older than all of you, right? So that tells me that something's going on with our weather. Look at the plains, right? The plains have gotten, over the past year, so much rain that it's damaged crops. Even here in Vegas, whether you think of it or not, our weather's been weirder and weirder, right? Our cold weather has been a little bit colder. Our warm weather's definitely been warmer, right? What's it been, 400 and some odd days since we had rain? Is that normal? No, it's not normal, right? We usually do get rain here, but we haven't been getting it. Tucson, same way. Phoenix, same way. Most of the desert climate, you can go down to something like the Salton Sea down in Southern California, right? That area used to be a lake. It's now completely dried up. Would that have occurred naturally? Sure, it would have occurred naturally in hundreds of years, not in the short time frame that we created it, right? Again, look at Lake Mead. That's another excellent example of showing that our temperatures are changing drastically. And then you add human consumption on top of that, and we end up with a fresh water shortage. Will we eventually come to a point where maybe water is our scarcest commodity? That's probably a good likelihood, right? Well, we say, well, then the ocean waters are rising. Why don't we use that water? Well, we don't have an effective desalination point right yet, right? We can desalinate water, sure, right? We can separate the salt out from the water and we can have fresh potable water and salt water or in salt. But then comes the question, what do we do with all that salt? Because it's going to be a lot of salt if we desalinate large amounts of water from the ocean. It's a viable option, right? What if we could take and somehow create a pipeline that starts in California in the oceans, right? And goes through a desalination plant, and that water then gets pumped into the reservoir here in Lake Mead. Why would California do this? Well, the reservoir in Lake Mead benefits them downstream, further down in Southern California, right? So it would benefit them, even though they would probably fight it and not want to pay for it. But that's beside the point. But the problem then becomes, how do we create an effective plant that can do that effectively? That's a major problem. We haven't come up with a way to desalinate water effectively. There are some desalination efforts in the Middle East that are working and are hoping to provide irrigation to areas from, using the Gulf and stuff like that as solutions, but it's still not effective. And then B, what do we do with the salt waste product? Because there is going to be a massive amount of salt byproduct. Some theories are, well, we take it to the salt flats and we dump it there because there's already massive amounts of salt there, right? But what does that do to the climate in that area then? Is it going to cause massive effects? Well, what if we dump it back into the ocean? Well, we can't do that because then we're going to increase the salination of the ocean and kill off the animals in the ocean. So we're kind of in a really stuck area here where we're increasing the temperature and our fresh water is decreasing. I went back to my home state a few years ago, and I drove by one of the lakes that I remember I used to go fishing and swimming in, and the water levels are drastically lower than they used to be. And they haven't gotten a real decrease in rain. It's still raining about the same, but consumption has gone up. And because consumption's gone up, levels are going down in our fresh water. And it's something we should really be concerned about that goes hand in hand with this climate change, right? Think about it. What do we use a lot of water for in Nevada? We use it for our pools to keep us cool because the air is too hot to survive in. So then it really begs the question, is the desert the best place for human survival? But that's another topic for another day, right? So when we burn fossil fuels specifically, right? When we burn those fuels such as, coal, oil, even natural gas to an extent, methane, we produce a byproduct of carbon monoxide, carbon dioxide, and some other chemicals as well. Those go up into the atmosphere, and those increase basically the weight of the atmosphere. When that weight of the atmosphere increases, that terrestrial radiation gets bounced back at us at a greater amount, right? Except where the energy is solar, wind, or water, increased consumption of energy adds heat to our overall, system here on Earth, right? So activities change the radioactive balance of Earth and change Earth's average temperature. Water vapor is one of the main greenhouse gases, right? We have that naturally, but that's naturally occurring in the atmosphere. CO2 is the most rapidly increasing in the atmosphere along with methane, right? Concerns doesn't stop there. For further warming by CO2 can produce more water vapor. So think about this, as we increase the CO2 volume in our air, more terrestrial radiation is going to be banged back against the Earth, which means more of the natural water sources we have are going to evaporate, which is going to further increase now the water vapor that's in our air, which is further going to increase terrestrial radiation, which is further going to increase the temperature, which is further going to increase the water evaporation. It's a vicious cycle that you can see, right? And then we add methane into the mix, right? Methane is released from various sources. One of the major sources that we produce for methane, honestly, is cows, because cows produce a lot of methane out of their rectum, right? They produce a large amount of methane from farting. This is why the meat industry is a major concern for climate change. And you hear people say, well, they want to take away your burgers. Maybe more ethically source them would be a good option, right? We consume more meat than we really should. And I'm first to admit that. I mean, I'm probably one of the worst culprits at this. But, when you think about it, the more meat we consume, the more cows we need. The more cows we need, the more methane that's going to be produced. And therefore, the more warm the earth is going to become. So the growing amount of all of these greenhouse gases is going to increase our terrestrial radiation that gets bounced back at us. So then that brings us to solar power, right? More energy from the sun hits Earth in 1 hour than is consumed by humans in the entire year, right? So solar energy can be a real life solution to fossil fuels, potentially reduce our dependence on them. And as a byproduct, we would reduce our greenhouse output. If we could reduce our dependency for energizing our cities by moving to more solar input and more wind input, right? And even some geothermal, rather than dealing with gas itself, but actually using the temperature changes between the undercurrents of the earth and the surface of the earth, we could actually theoretically reduce our requirements and a use of greenhouse gases. Are we ever going to get there as a country? I can't answer that, right? I don't know. It's going to be on your generation more than it's going to be on my generation to change that. Because my generation at this point pretty much has thrown in their towels and are full QAnon believers at this point. But your generation has the chance to do this. Whether you like it or not, climate change is real. It doesn't matter what your crazy Uncle Bob posted on Facebook that, well, climate change is natural and it's been occurring. There's nothing we can do. Right. We can't stop climate change. You're exactly correct, Uncle Bob. You are 100% correct, even though you're believing QAnon. But we can slow it down. And if we don't slow it down, your children are going to pay for it. Right? My generation's pretty much done. Face it. We're just a step away from being in a nursing home from you all taking care of us. Right? It's your generation that's going to change things. Well, how do we change things? If this is something that scares you, and it should, don't get me wrong. If it doesn't scare you, well, then, okay, maybe you just, A, either don't understand it, or B, just don't feel that is that big of a concern for you, right? If it doesn't scare you, then I can't help you there. That's just, there's nothing I'm going to say that is going to change that at this point, right? But how do we change this? Well, we change our dependence on things like gasoline, right? We build more fuel efficient cars. We also have to look at, if we go to something like electric or hybrid vehicles, how do we offset the waste that we're going to produce in those vehicles as well? Because we're going to have battery waste at that point, right? We also have to stop things like the lithium mining that's going on in certain areas where it's child labor and stuff like that. That's beside the point. We have to look at, is there more efficient fuels we could possibly burn in cars? Could we be burning them using a hydrogen engine, which is one of the areas we're looking at, right? We talked about that, using water as energy. It's a possibility. Are we still always going to need things like trucks and trains, stuff like that, to transport materials across country? I'm sure. But could we make them more efficient? Could they use biodiesel maybe and use waste products as their diesel source? Possibly. Right? But this is where you have to think about this, because in reality, we're at a tipping point. And if you talk to some scientists, we're beyond that tipping point. We're at the point where we're now on the roller coaster going down, and the only thing we can hopefully do is put some brakes on the roller coaster, right? There's always the disaster movies always come out after this, right? If you've seen like The Day After Tomorrow or something like that, right? Those disaster movies are looking less and less like science fiction and more like science fact, right? Then if you again go back to your crazy Uncle Bob will say, we're more likely to die from a meteor strike than we are from climate change. Well, a meteor strike's a viable thing, right? But what Uncle Bob's not thinking about, Uncle Bob's thinking about his own self, right? And we have to think more globally, because one of the things, the side effect of this is going to be is food shortages. We're already in a case where here in America, 1 in 5 families are food insecure. Think about that for a second. 1 in 5, so 20% of us are food insecure. Now let's change that. And now we have food shortages where only the people that are the most wealthy can attain food. It's nothing, it's not going to be crazy to say that 2 in 5 or 50% of our population becomes food insecure. Does that mean we don't have food? No, food insecure doesn't mean we don't have food. It just means we don't know where our food is going to come from, right? We don't know where our next meal's coming from. And so then we're going to end up in a situation like that. And then we're going to end up, that's how global conflicts start, right? There's been tons of global conflicts over natural resources. Think of all of the Gulf wars that we've had. Any war that we've had in the Middle East has been pretty much over natural resources or religion. But we're not going to get into that topic today either, because that'll set Mr. McKeever on a totally different rant. But almost all of our stuff, natural resources, either oil or uranium, plutonium. Yeah, oil in most of the Middle East, Afghanistan, Iran, Kuwait, all of that. And then plutonium and uranium in the northern parts of the Middle East, in Afghanistan, Pakistan, stuff like that. So this is scary. This is real talk here, folks, right? So now if we look across the globe, it becomes a lot more difficult because, we may think about people being food insecure here in the United States. There are people, again, you see the pictures from Africa of people that are not food insecure, that have no food and are starving. That can be a realistic thing that could happen here in the United States. And what could drive that? Climate change, right? What happens if we lose 20% of the United States due to rising seawater? Well, the population is going to have to move inland. Well, the population inland is primarily our food sources. So now we move population inland, have to build houses on those areas where we really used to produce food. And now that production of food goes down. But we're not going to stop reproducing, are we? No, we've got people that have, I just saw a picture of some family in, I think it was New York or whatever, where they have 14 boys and their 15th kid is now a girl. That concerns me. That's population increase, right? I'm not going to tell you not to have kids. That's not what Mr. McKeever is here preaching. I'm not saying that. But the more people we have on this planet, the more mouths we have to feed. The more people we have on this planet, the more greenhouse gases we're producing. Because even as human beings, we produce methane, right? Go eat a good broccoli and broccoli chicken or something like that, and you'll produce tons of methane, right? Go eat some beans. You'll produce some methane. So how do we fix this? I don't have the answer. I'm not smart enough to have all the answers. If I was, I probably wouldn't be teaching at Pima, right? I'm not smart enough to think about that, but I know enough that it kind of scares me. And this is just being honest about this, but all this comes back to the law of thermodynamics. Right now, energy is being driven into the system by the sun, right? So 2 options can occur. The internal energy of our planet can increase, or work can be done by the planet, right? And I don't see us speeding up and spinning faster, although that's a possibility as well, but that's beside the point. So what's going to happen? The internal energy of our system here in the world is going to increase. That means temperature is going to increase because the atmosphere itself is not going to expand. That would be something that could help us. If our atmosphere magically expanded by 10 miles, that could potentially help us. But that's not magically going to happen. That doesn't happen just spontaneously. So that means our internal energy of our system, based on the law of thermodynamics, is going to increase exponentially. As everything increases, the temperatures are going to increase here. We're going to get more drastic temperature changes. Areas that are cold may get colder. Areas that are hot are going to get hotter. Then those areas of cold are going to melt as well, which are going to change drastically the face and the structure of most of the continents on the United States or the world. It's nothing to say that the continents themselves may not shift together. We don't know what's going to happen with plate tectonics because of this. So does that mean you need to stop driving your car? I don't know. I don't have the answer here, right? I don't. And this has been about a 15-minute rant here by Mr. McKeever, so I apologize if you're bored at this point. But this just shows how this comes back into real life with us. So then how does this play into with physical therapy? Well, I mean, a lot of this plays into physical therapy, right? And the reason being we use heat usually on a daily basis with patients, whether it's a hot pack, whether it's getting them warmed up, whether it's using something like ultrasound, which we'll talk about how it converts energy to heat. So thermodynamics is a pretty large portion of what we do as physical therapists and physical therapist assistants. If you don't understand how heat is transferred, you'll never understand how that heat helps the human body, right? So if we increase the temperature of a bicep, right, we increase its internal energy and therefore it can do more work. So that's why we want to warm up our muscles. If we warm up our muscles, they're able to do more work. And that's ultimately what we want in physical therapy, isn't it? We want the patients themselves, to be able to do more work. So heat and the transfer of it and the law of thermodynamics and everything comes into play. And then we go back into, like I said, the diet. The only diet that follows the law of thermodynamics is calories in less than calories out. If we follow that diet, we are guaranteed to lose weight. It's just scientific fact. Our body cannot do more work if it doesn't have the energy to produce it. So it increases caloric intake. This is why also that there's a misnomer that says that cardio burns fat. Cardio doesn't burn fat. Cardio burns calories. Doesn't matter where those calories come from. Cardio may burn calories from burning muscle, right? So it's not always going to be, it's not like doing cardio is selective. So cardio alone is not going to change your body's physiology. The only way to change your body's physiology is by increasing your caloric outtake, right? Your energy use. Also changing your diet and adjusting your diet so that your food that you're intaking is more conducive to the mass that you want produced on your body, if that makes sense. All right, so I finished this with, oh, look at that. It is, currently 10:34, so I have about 26 minutes left before let's stop sharing here, before they shut off my electricity. So I'm going to get this video encoded. I'll send out a message here shortly just telling you guys that I appreciate you being flexible with this. I didn't expect them to be coming by to turn off my power. I don't know what they're doing outside. I don't question Nevada Power and Light. But if you have any questions, please shoot me a message. Otherwise, please stay safe. And I will see you guys on Wednesday at our normal class time. Thanks for being flexible. I will catch you guys later.